The definition of equilibrium is when a reaction takes place at the same rate as its reverse reaction. So we have a forward reaction and we have a reverse reaction. And so these are the reactions in which you will see a double arrow between your reactants and your products. So depending, it could go either way. When equilibrium is reached, there's no net change that is occurring during that reaction. And so you're getting no more reactants and no more products, but they're still moving back and forth. And that is called your equilibrium state. And so when it's in the equilibrium state, that is when we use the double arrows. Now, sometimes you are going to see a double arrow situation where one arrow is heavily darkened versus the other arrow. And that's just telling you and showing you which side is being favored at that time. And we'll talk about the favored direction and what that looks like in the third video with Le Chatelier's principles. Now there are two systems that we can look at for equilibrium and track equilibrium. Looking at physical systems first. So we're going to put bromine, and bromine's a liquid in its natural state, into a closed container. Now bromine is an extremely volatile compound, and volatile means that the boiling point of bromine is very close to the room temperature, and therefore it can move to its vapor state or its gaseous state very easily. So you're going to have particles moving to its gaseous state without heating it any more than usual. So what happens to reach an equilibrium state is bromine liquid evaporates, which means it's going from its liquid to its gaseous state. Now gases move around because they have increased kinetic energy, and we understand that. Some of those gases are going to hit the liquid surface. And when they hit that liquid surface, they are exchanging some of their kinetic energy to the liquid, and that's going to cause them to condense and go back into its liquid state. And so what happens at equilibrium is you are going to see the evaporation equal the condensation. And when that happens, we have reached an equilibrium state. Now what's nice about the bromine example is bromine it's a purplish black color, and so at first when you put the liquid in there, you can see it's clear through the glass. But over time, the atmosphere of the glass, the air in the glass, turns into that purplish black hue. When that hue no longer changes color, that's when you know it has reached an equilibrium state. There's a graph they can use to represent this. And so we have time of the reaction and we have the rate that is occurring, because equilibrium and rate go hand in hand. So we know during this process we're going to see an increase in, for us, it would be the product, because we are going from bromine liquid to bromine gas. So our product is going to be bromine gas. So this arrow, or this line we just wrote, that is the rate of condensation. And then up here, this is the rate of evaporation. When they reach each other, or meet right here, at this point in time that you see the two go flatline, that is your equilibrium state. And I spelled that wrong. And so it's just a way in which to represent, and we're going to see these graphs a little bit later as well with the chemical systems. So speaking of chemical systems is literally looking at the chemicals that are in there, not just seeing physical changes like color change, bubbling, precipitate formation, any of that. That's all physical. Chemical is what's actually there with the reactants. So here we have 2HI, and it is going to go in between H2 gas and I2 gas. Now what's nice about this, we have two colorless gases, and we have purple when iodine gas is being formed. So we have something physical that we can go through and track. So our forward reaction is when reactants go to products. The reverse reaction is when products go to reactants. Now we call this dynamic. And it's dynamic due to the fact that they're going to occur at the same time. Reactants become products and products become reactants. Now when we go in the reverse, we still say the products are going to the reactants, just so we always know what compounds we're talking about within a reaction, and we try not to confuse ourselves. So what can happen here, and the way to represent this, if we have a graph to watch this reaction over time. So we have our time, and we can track concentration as we learned with rates. Well, if we go through and we look at this, and we have HI, well, HI is our reactant, right? And so we expect it to, we expect to have it to start with, right? So we would see it and we expect it to decrease, right? And then we have our product formation and we expect it to increase. So here we have our H2 and I2, and we have our HI concentrations. Now the point of equilibrium is when you see the lines go flat. And so at that time, when they are flat, that is your equilibrium mixture. You could look at this from a different point as well. So if we have time, we have concentration. So let's say we started with our products and we're going to do the reverse reaction. So we have a lot of our products made. Well, we're going to see those decrease over time, and we're going to see our reactants increase over time. And so essentially, what all this shows is no matter your starting point, reactants or products, you are ultimately going to get to the same equilibrium mixture. So once again, here's the time where equilibrium is reached, and here is your equilibrium mixture. And they're going to be roughly, not that I have a really good graph, but they're going to be roughly at the same amounts as if we started with reactants first. And that is what the mixture is. So you can start with only reactants or only products or a mixture of the two. But as long as you're under the same conditions, the same equilibrium mixture will be created. So there are 5 characteristics to this equilibrium state. First, equilibrium is dynamic. That means the forward and reverse reactions occur at the same rate. And you'll see no net change in the system at that point. Second, equilibrium can only be achieved in a closed system. Because by being in a closed system, that's going to prevent the exchange of reactants and or products with the surroundings. And so that only allows those reactants and products to react and or recombine, do whatever they're doing in their reaction with no other interaction and no loss. Because a lot of these times we're working with gases and we could lose the gases. And therefore that would not allow for an equilibrium state to be achieved because you're constantly having a loss of compounds. At equilibrium, the reactant and product concentration stays constant. It does not change. So the the products are being produced and destroyed at the same rate. So we see no net change in the concentrations if we are to measure them at this equilibrium state. There's no change in macroscopic properties. Macro means large, and so that's something that you can see with your naked eye. And so there's no change in macroscopic properties because macroscopic properties are dependent on the concentration in the mixture. Like we had discussed with our bromine example, that when the atmosphere within the bromine no longer changes to a darker purple or a lighter purple, it stays the same. You know you've reached the equilibrium mixture and it doesn't change in its macroscopic properties. Lastly, you can reach equilibrium from either direction. No matter your starting point, equilibrium will be at the same point as long as all the reactions are done under similar conditions. Lastly, at equilibrium, the constant concentration does not necessarily mean equal. You don't have to have the same amounts of products and reactants to be at equilibrium. It all depends on the conditions the reaction's running in, what's being formed, how many molecules are present, complexity of the molecules. There's a lot of things at play. So very rarely are they going to be equal at the equilibrium state. One side may be favored, and that's all going to depend on the reaction and its conditions. And so we call this favoring equilibrium position. So if products are favored, that means the equilibrium position is going to lie to the right, to the product side. If reactants are favored, that means the equilibrium position is going to lie to the left, or the reactant side. We can determine this mathematically. And guess what? You're going to learn how to do that.